And I would like to welcome you to the 10th lecture in CFD. Today, as I said, it's just 1 hour, and then the second hour would be about the homeworks. As usual, I would like to summarize very briefly what we did in the previous time, and that was actually yesterday afternoon, so it's not so long time ago, but still it may be good to kind of just recapitulate what we did. So we looked at yesterday we derived the Navier-Stokes equations and then the Euler equations from that, together with the equation of state and so on. And we realized that in principle, the governing equations for compressible flows can be written as a conservation law, as a nonlinear conservation law, essentially in the form as I indicate here. We have then realized that there is different ways of writing this nonlinear conservation law. Now I'm doing it here in a 1D problem, but of course it could be also in multiple dimensions. But essentially, we could identify two different ways. One is the so-called conservative form, where we essentially write the time derivative plus a space derivative is 0. But then we have also seen that by using the chain rule, we could come up with something that we called the quasi-linear form, where we again have the time derivative, but then we have some speed f prime of u or outside of the space derivative of u, of the unknown quantity. And in this way, with this quasi-linear form, we could then identify also the type of the equation by doing the eigenvalues, or in this case by just taking that f prime value, and we could see that this f prime is exactly the slope or the speed of the characteristics. So therefore, what we take out of the bracket is really a speed. If you think of Navier-Stokes, or well, maybe not only Navier-Stokes, but there's also other names that people have used for these different ways of writing the equations. So for instance, the conservative form at times is also called the divergence form of the equations. And of course, the reason for that is kind of obvious, because you actually do a divergence of the fluxes as part of the conservation, or to enforce the conservation properties. So divergence form is another word. And the quasi-linear form, because you take out the convection speed, is at times also called the convective form of the equations, because you kind of take out the speed explicitly. But in the end, these are the same. It's the same thing as written here. And also, and that's I think important, on an analytical level, all these forms are exactly they're exactly the same. It's only when you start to do discretizations that it starts to matter what form you look at. And we will later also see an example where there will be problems by using, for instance, the quasi-linear form. Anyway, so this is the way that we could write the nonlinear conservation laws. And then we have done a number of examples. The first one was just the advection equation, where, of course, we could see that the f prime would be a, and f of u would just be a times u. So you have a simple convective flux a times u. But the second example is where we stopped, and that's of course a little bit more interesting, and it will also essentially keep us busy for today, because the features of the second example are really what we also discuss or observe in Navier-Stokes or in the Euler equations. So that's type of behavior is exactly what we have in our fluid flow equations. And the Burger's equations are that example, and they were exactly designed in order to be an example or a test problem for Navier-Stokes. They may not have all the properties. So for instance, there's no pressure. In this way that I wrote it here, there's no viscosity. But at least the nonlinearity of the Burger's equation looks very much the same as the one for the Navier-Stokes equations in just 1D. So that's why we typically use it as such. So the flux function for burgers is u squared divided by 2, which then gives you a slope of the characteristics, or this f prime of u, which is simply u. So that means if I want to write them in the quasi-linear or convective form, I get this equation here, where I can directly identify that the speed of the characteristics essentially is u, which then gives me the idea that the solution is advected with the local speed of u. Of course, this is a nonlinear problem now. So that means u, so the convection speed actually depends on the solution and may change as we kind of move on through the simulation. So let me now illustrate to you what that actually means for a specific initial condition. And this is what we were plotting yesterday as the first example. So we had the idea that we have a space-time diagram. So we have an t-axis here, and we said that at t0 we plot the local or the solution at t0, which looks like this. So again, keep in mind this is kind of the solution plotted inside a space-time diagram. I just do it in that way because that's easier to plot than trying to kind of come up with a 3D type of plot. So this is the solution at time 0. And now the question is, what happens at time t1? So later on. And what we have seen yesterday is that the solution that was 0 at time 0, of course, that solution will just propagate with a slope of 0, or actually, if it's in this plot, it would be a slope of infinity. But essentially, without changing its solution, it will propagate just along the t-axis. So something like this. So that means then at the end that at t1, at these points here, I will have exactly the same solution I had before, namely the solution 0. Take away all these yellow bits again. So that means what we have already understood for now is that the new solution at t1 for that bit and that bit would be 0. There was a question whether u isn't on the vertical axis. Now I'm not fully understand what is meant. I mean, there's two coordinate systems in green indicated here, one here and one here. This is the typical way that I would plot the space-time diagram. It's just, as I said, it's to avoid trying to plot something in 3D. I mean, I can try it in 3D. If this is x and then t would be like this and u like this, then this could be, t0 and this would be t1, something like that, and then it would be like this. And then at a later stage, it would kind of be like this. Okay. So this would be now the 3D representation. It's a little bit more difficult to make. That's why I try to do it in only 2D. But I mean, if you want, you can view it like that. Okay, so that means what we have here it was 0, here it was 0, so it was just propagating like this. So it would be 0 and 0. That would correspond to these two lines. Now, okay, good. Then let's now try to see what happens in between those 2 points. So from here to here. Now, what happens there? So first of all, let's just take this point perhaps. At this point, I have a certain speed, which is, I mean, I have a certain function value, which is maybe not large, but it's more than 0. So that means at that point, I will have a certain speed of the characteristics in the positive direction. So it's not vertical anymore, but the slope is kind of tilting a little bit to the right and having a certain speed. So that means that solution will later on be at this point. So if I try to now plot the same height as I had here, it would be like this. And of course, that point is still the same. So what we can assume that if I do the same thing also here, now I need to be a little bit careful. So that's maybe slightly more inclined slope, something like this perhaps. And at that point, I will have this speed, something like that, or this value, something like that. So that means that this line would then afterwards look like this line. It would kind of have stretched into the x direction. If I now try to do that also in the 3D plot, the idea is kind of the same. I would get something that has, you know, stretched kind of, you know, you will have these characteristics being more and more leaning to the left, to the right. Okay. And of course, on the way when it goes down here on that side, you will have kind of the same. You will have a high speed here and a lower and lower speed here up to the speed 0. So that means you will get something like this. And then if I do that also in the 3D plot, you know, maybe a solution like this. So that means my triangular tip or symmetric tip that I had at T0 was then slowly kind of, you know, tilting over to become more and more steep. Okay. Now, okay, now I'm here at where the tip is like this. What happens later on? So maybe at this time, so or in the 3D plot, it would perhaps be, you know, somewhere here. So the later times, again, these ones would continue the same, this we know. So that means in this case, these ones would remain or would continue the same. So the question is, what happens? Well, this tip here would of course continue to kind of, you know, lean to the right. So that means at some point, and that's now the issue, at some point these characteristics from the center would start to hit the vertical characteristics. But at this point, the ray starting from the center would hit this line. Also this we can try to plot here in the 3D plot. We'll kind of go on, and then at some point it will hit the vertical line from the straight characteristics. And of course that is a problem, because that means at this point I cannot kind of use my typical way of how I would construct a solution in a hyperbolic problem, because typically what I would do to find the solution in the point, I would just go backwards and find out what the initial condition was. That's what we discussed before. But if I'm at that point, I actually don't know how to go backwards, because I could either go along this inclined line or I could go down straight. And of course, I could then choose what solution I would get. And that's not a good thing. So what actually happens here is that I get something that is called a shock. So two solutions collide. With each other, and that means that I need to find a different type or a different way of creating the solution to my problem. So this is called a shock, and that will cause a discontinuity in the problem. Let's just write that down. What we have. So, or in the beginning there is not a big problem, but at some point we have a crossing of characteristics. And that means that I may have discontinuities, or discontinuities may develop in the domain, and this then causes a shock. We will discuss later on exactly what we mean with a shock and how to also calculate it, because we can still do something. It's not that everything is lost. But we get these shocks. And the important thing is that all this happens despite the fact that my initial condition was actually quite harmless. So despite having smooth initial conditions in the beginning. So the initial condition that I looked at was just this, this little triangle. It could even have been a sine wave. It doesn't matter. It could be something very, very smooth, infinitely smooth. But the fact that I'm using a nonlinear conservation law to advect my initial condition in time leads to the fact that I may get discontinuities. And this, in fact, is a very common feature of. So this is a feature of nonlinear conservation laws. Namely that the fact that you can actually have discontinuities appearing due to the action of the nonlinearities, due to the action of the different characteristic speeds, even though your initial condition was completely harmless. And of course, that means now for the numerical scheme, we need to have something, we need to have schemes that can actually deal with the fact that suddenly you get a discontinuity in the flow. So that would mean general methods like spectral methods, which are based on a Fourier expansion, for instance, that would not really work because they would have then wiggles all over the place and would essentially blow up. So we need to have methods that can deal with the fact that discontinuities appear. And we will see now a few methods that can do that. And also in homework number 4, you will solve yourself a case where you have a shock appearing. And then you will see how these methods then work. Okay, so this example now kind of served as an introduction of what the problem is. But now we need to, of course, study a little bit in more details, in more detail, the appearance of these shocks and how we can actually understand it a little bit better. For this, what we do is the following. Let's study a so-called Riemann problem. And this is just a name that has been become common in the study of these nonlinear conservation laws, which is actually, it just means that we isolate the region around the discontinuity and we see what happens depending on how this discontinuity looks like. So I'll tell you in a second what this is all about. So we take our governing equation, ut plus f of ux is 0, and we focus on Burgers. So this the Burgers flux is u squared divided by 2. So it's exactly the same equation. But now for the Riemann problem, we now say we consider a very specific initial condition, and that is with just two values, ul and ur, and we say that it's ul for x being lower or equal 0 and ur for x being larger than 0. And we assume for the first case that ul is actually larger than ur. So our initial condition would look like this. So if this is x and this is u, then the initial condition would be something like this. So it should be vertical and like this. So this is ul and this is ur. So we have one jump, one discontinuity in the initial condition. And it's now done in that way that ul is actually larger than ur. So the initial data has only two distinct values. And this is, as I said, a so-called Riemann problem, because it really serves as a test problem for numerical algorithms. So you use this as an initial condition, you let your numerical algorithm kind of treat it, and you will see how well it approaches the exact solution. So for us, it means now we need to understand what is really the exact solution of this problem, because that helps us then to understand how a numerical scheme should be able to handle that. Yeah, what is now what is the exact solution of this? Okay, well, we know that we have characteristics. So we have characteristics, and these are lines with slope, well, lambda being dx over dt, being f prime of u, which is u, as we know from before. So again, if I just draw that now in again a space-time diagram, but now I'm just doing it in 2D. So I look from above, and now I try to do that in a good way. So on this side, we have as the initial condition was UR, and on that side, the initial condition was UL. So that means in the UR part, because it's a little UR is lower than UL, so we have the characteristics, or the characteristics lines are maybe, you know, something like this. Okay. Now on the left side where we have UL, we also have characteristics, but the speed is larger because UL is larger. So that means they lean a little bit more to the right. So now I need to see that's maybe something like this. You know, lines like this, perhaps. Okay. And now we have seen that that there is an issue because, and you can kind of see it already now. You know, if I continue, for instance, this line and this line, you know, at some point these two guys they collide with each other, and that's where we have a shock. And of course, that's not the only ones that collide. There's also some other ones that collide. Maybe this one collides here, and then we have these guys colliding here. And if we combine all of these colliding characteristics, what we get is a line here. Okay, that should be straight. Starting from, of course, the original position of the discontinuity, and then it's a straight line with a slope, which is s. We will derive the size of s in a second, or not derive, but we will write it down. And this red line, now I would consider to be the shock, or the position of the shock, because there is at each point along the red line, we have two characteristics running into the shock, and essentially being dissipated into the shock. So what you see from this graph is that what happens really is that the discontinuity that was located here at 0, remember, this was the discontinuity at 0 at first, is essentially just traveling from 0 with a certain speed to the right. And the speed of the shock is this s. So what we can say is we have a shock with a speed. So the shock, or the speed of the shock is s. Is s, and this s is actually given by a formula. Given by a formula, and this is the so-called Rankine-Hugoniot condition. And this condition is quite simple. It says that the shock speed, so s, which is dx over dt along the shock, is f of ul minus f of ur divided by ul minus ur. And this is valid for the Riemann problem that was written exactly in the way that I shown here. So we have two values, ul and ur, and then the shock speed, the shock speed is then given by this formula. If we put in the flux function from Burgers, which we know that f of u is u squared divided by 2 for Burgers. If we put that in, and then you will actually see that for Burgers, the result for the shock speed will actually be very simple, just 1/2 of UL plus UR. So that means in case of Burgers, the slope of the shock will just be half of, or will be in the middle, exactly in the middle between the slope of the right side and the slope of the left side. So something kind of that I try to indicate here. This result is only for Burgers. The correct result essentially would be this one. As I said, this is the Rankine-Hugoniot condition, which I just write down here as a result. The derivation of the Rankine-Hugoniot condition is not difficult. It takes I don't know, it maybe takes 10 minutes, 15 minutes to understand. I would not like to do that now in the lecture because it may not be fully relevant. But if you are interested in the derivation is written in the lecture notes and you can follow it. It's, as I said, it's not very difficult, and I would say it's enlightening in the fact that you will see that in the end it's quite straightforward to get it. The basic idea is that you will make a little box around the shock, and then you will see with the slopes that come, the 2 slopes from the sides that come in, that the slope S needs to have this specific form. So the derivation for the Rankine-Hugoniot condition, just I refer you to the lecture notes, or of course any book that you would like to. Okay. But that means actually with just a few lines, we have come up with the exact solution of this Riemann problem here. So we know that if we have a discontinuity at 0 that looks like this, well, what happens in the future is that the whole thing is just moving to the right with the shock speed s. So that means the exact solution is now like this. I just do it first graphically. So if I have again an XU diagram, and I start with the initial condition, which was something like this, then I know that this shock here will just move into the positive x direction with a speed s, and this distance here would be s times, well, we don't need to have a capital T, actually, we could just write a small t here, s times t. And formally written, u of x and t would be still just ul or ur, but what changes is that ul is valid if x minus st is lower than 0. It was lower equal, wasn't it? Yes, lower equal, and UR for x minus st is larger than 0. So that's the exact solution for the Riemann problem with a shock. So actually, it's the shock solution that we have seen here is not the very difficult one. It's just a shock moving to the right. Okay. Now, but that was just one, or maybe I should mention 2 more comments here. So the first of all, which sometimes is a little bit confusing, the shock speed s is not a characteristic speed. So it's not the speed on the right or the speed on the left. So we have the shock moving with a different speed than the two characteristic or the characteristic speeds. And that, of course, that's something important. So we have something in the flow that actually moves at a different speed. It's a combination. It's based on the characteristic speeds, but S itself is not the characteristic speed. That was the first comment I wanted to make. The second comment I wanted to make is we kind of need to make sure that the solution that we have now obtained, which we kind of just sketched and maybe a little bit with hand waving, we still need to make sure that this is actually a solution that makes sense from a physical point of view. That means since we deal in the end with physical problems, we need to satisfy certain physical properties. Even when we have discontinuous solutions. So what I'm kind of meaning is that the starting point to all of this was this graph here when we said that, oh, at some point we suddenly have two characteristics and we don't know which one we should follow. So what happens? So we have a solution that is essentially it's not unique anymore, or at least we could think it's the solution is not unique anymore. So that means there needs to be something that decides which solution is actually correct. And the typical physical principle that we would like to invoke here is the so-called entropy condition. So this is something that is relevant for making sure that the mathematical solutions that we get are actually physically sound solutions. We will see in a second an example where this is important to understand. But before we do, I would like to introduce very quickly what kind of the idea is with the entropy condition. It's a kind of a halfway physical principle. We assume that the entropy is kind of this concept of the disorder or a measure of the disorder of a system. As you know, disorder of a system in the sense that there is certain forms of energies that can go into each other, but not the other way around. I mean, it's essentially it comes from thermodynamics, the second theorem of thermodynamics, which means that you can only increase the disorder of the system. So that's the principle that we would like to invoke here. So what this disorder for us means from a thermodynamic point of view is that the entropy indicates how much of the internal energy, in a system is available to do useful work. Of course, what useful work would mean, that could be, for instance, increase the pressure in a region or decrease density, for instance. Now, if I just would like to indicate what I mean with that, if I have a diagram here where I have X and I have T and I have a shock here, or just a discontinuity, and I have two regions, S1 and S2. So actually the letter for the entropy is S. So now the idea is, if I go from this point, so if I'm located at a certain position X, and I go to another point from one region from S2 into S1, So from a region with an entropy S2 into a region with an entropy S1, and I go over a shock, that means, or the idea now of the entropy condition is that the shock can only increase my disorder of the system. So it means that the entropy condition here would mean, this was the shock, would mean that S1 needs to be larger than S2. And what it means for me as being a flow property in the region of S2 or S1, it could mean that in S2, I would perhaps have a low speed, which then could be transferred into large speed when I go from S2 to S1. Or if you could also then consider it from the pressure. So you would go from a low pressure to a high pressure region, for instance. So that's what would happen when I go from one region of from one entropic region S2 to another one S1. Now, what it means for different flow situations, now this entropy condition, is that in the case where I have a smooth flow, so for instance, I just, I go from this point to this point, inside the same region, I do not meet any discontinuity. Well, in that case, it would essentially mean that the entropy is constant along a fluid path. Constant entropy means isentropic. And of course, that just means that if I just move from this point to this point in a smooth flow, so a flow where I have a normal mathematical solution without any discontinuities, I actually do not need to consider the entropy condition, because the entropy doesn't change and it will not give me anything. But the problem is over shocks. So when I have a situation where where I have a flow discontinuity, so if I go from here to here and I cross over a shock, then I know that crossing over a shock means that I need to have an increase of entropy. So over a shock, entropy needs to increase. Okay, and now we need to think a little bit. What could we use to indicate the fact that the entropy increases over a shock? And the conclusion that we can come up with is a condition which says that f prime of UL should be larger than the shock speed s and should be larger than the f prime of UR. So if this is now speed UR and this is speed UL, if I go over a shock, I would like to have my entropy increasing, which means I need to go from f of UR, which is the speed there, through the shock speed to UL. And that would indicate in the end that I have an increase in entropy. And this last condition here, this would be the entropy condition, which tells me whether or not a shock in a specific configuration is in fact something that fulfills the second law of thermodynamics, so that entropy is increasing. Now, having said all of this, let's now check whether this entropy condition holds for the solution that we have just derived here for the Riemann problem. So for our Riemann problem, well, what we see is actually there we have UL, which is larger than 1/2 of UR plus UL. which is larger than UR. Because, and this is true, because we have assumed in the beginning that UL is actually larger than UR. So that means this is actually okay. So we have our shock solution has fulfilled the entropy condition. So this seems to be a very good solution. Okay. So far, so good. But now let's do one more thing. Let's do the opposite. Consider the opposite Riemann problem. That's now the last thing that we do for today. Well, the opposite Riemann problem would be like this. I have, again, my initial condition, but now it is such that UL is lower than UR. Yeah, let me again draw the same space-time diagram where we have X and we have T here. Now it is like this, that UL is a little bit lower, so my slopes of the characteristics are maybe like this on that side where we have UL, and on that side when we had UR, it's maybe a bit like this. So now the question is, what happens in this region? What happens in this solution, in this hatched region? What is the solution there? Well, maybe the first idea that I could have would be, I can define in the same, exactly in the same way as we did here. In the same way as we did here, we could create a shock solution or construct a shock solution, something like this. Well, shock solution would then look like this. Again, X and T. I had my lines like this and like this. So I would create the shock, maybe with a shock speed S, and then I would say that I get, lines like this that would come out. Then the direction of the characteristics obviously would be like this. So this would be a shock solution for this Riemann problem. Now, as I just said, we need to have something that is physical, and this is a discontinuous solution, so I need to check whether this would fulfill my entropy condition. My entropy condition says, well, UL needs to be larger than 1/2 of UR plus UL, which needs to be larger than UR. Of course, if I kind of do that, then I will see that UL is larger than UR for the shock to be physical. Of course, what we assumed was UL is lower than UR, but now we see that the shock would require UL being larger than UR. And of course, that doesn't work. So that doesn't agree with each other. So that means that my shock that I just drew here is not a physical solution. Solution violates the entropy condition. So it doesn't fulfill the entropy condition, which means that there would be actually an increase in entropy when a decrease in entropy when you go over the shock. And this, of course, is not something that is allowed from the second law of thermodynamics. Well, but we still need to have a solution to the whole problem. Well, so that means if we cannot do a shock solution, we actually need to come up with a smooth solution. And actually, it turns out that this will also be the correct solution, And I just draw that now like this. So if I again have the two regions from before. Well, what could be a smooth solution? Well, it just means that I could have in essentially just additional characteristics that suddenly appear here, which just smoothly lean from the higher slopes to the lower slopes. So that is actually the solution that will happen. And this is a completely smooth solution. There is no shock, there's no discontinuity appearing here. So this will be a smooth transition from the slope of the characteristics with UL to UR. And the solution that I get here, so this red kind of wavy thing, there's a number of names for that. It could be an expansion wave. It could be a rarefaction fan or an expansion fan, things like that. It just kind of, it fans out the solution and it becomes smooth. If you just let me finish this for one more minute. As I said, this is a smooth solution. This is a solution in the classical sense. So there is no discontinuity, which also means that actually, because there is no discontinuity, we do not even need to satisfy now with this solution. So no need to satisfy a entropy condition, because it's isentropic. There is no jump. There is no discontinuity condition. Okay, now how does the solution look like? So the exact solution, well, even that I can briefly draw. We had it before. So if I have UL and then UR, this was UL, and if this now evolves over time, well, we know that this point here will move to the right with the speed of UL, something like this, up to that point here. So this point travels with the speed of UL. This point here travels with the speed of UR, so with a faster speed, up to that point perhaps. Speed UR. And in between, so from this point to this point, we will have a straight line which corresponds to this expansion fan. It needs to be straight because all the waves, they start in the same starting point, in the point of discontinuity at time 0, but then it just fans out smoothly. And this is, as I said, a classical solution. There's no discontinuity. So that means we have now seen two Riemann problems, one where UL was larger and UR smaller. Then we get a shock which moves with the shock speed, and it has to fulfill the entropy condition because it's a solution with a discontinuity. And we have seen this one here, which is the Riemann problem when UL is lower than UR, and then we have a fanning out of the solution happening over time. So these are the two solutions that we will get for the Riemann problems, and with this, essentially, we can construct all different solutions for the Burger's equation or any nonlinear conservation law. And as I said, knowing how the solution looks like is very important, because now the next step would be to design numerical methods that can actually take care of this. And also homework number 4 will be something that looks at this. Okay, with this, I would like to close for today. I'm sorry that there were 4 minutes late, but I thought it was important to conclude this. Now you will start with Fermin and Luca for the homework, and we will see each other again next week for well, numerical methods for this. Okay, thank you very much.